warahmatullahi wabarakatuh. Today, we will continue our chapter 3 on basic equation in fluid mechanics. Okay, application of Bernoulli's equations. 1. Water discharge from an orifice. 2. Velocity measurement using a pitted tube. And flow measurement using meter venturi. Okay, example 9. Okay, a large tank with open to the atmosphere here, filled with water to a height of 5 meters from the outlet tap. Okay, this is a tap. So a tap near the bottom of the tank is now open and water flows out from the smooth and rounded outlet. Determine the water velocity to find the velocity at the outlet. Okay, at this outlet. Okay, so the solution here, using the Bernoulli equation, P1 is equal to P2, pressure at 1 and pressure at 2 is equal to 0 because it's at atmospheric pressure. So Z1 minus by Z2 is the height h, and the velocity 1 is 0 because it's open to the atmospheric pressure. So you use the equation for the Bernoulli. Pressure at point 1 and the pressure at point 2 at the inlet. This is inlet and this is outlet. Okay, so P1 is, okay, this is 0. Okay, and P2 is also 0. Okay, and V1 is also 0. So Z1 minus by Z2 is the H. Okay, this is a H. So just only have the velocity 2 over by 2G. So this called Torricelli theorem. Okay, to find the velocity at point 2. So velocity of flow at depth of h is 5 meters. So you get, insert all the value here. So you get the velocity 2. Okay, so the velocity at point 2. Okay, so we get 9.9 meter per second. Okay, look at example 10. So a closed tank here. Okay, the closed tank has an orifice. Okay, this is orifice here. Okay, with 0.025 meter diameter in one of its vertical side. Okay, this is orifice. Okay, the tank contains oil to a depth of 0.61 meter. Okay, the oil contain oil here. So above the center of the orifice, so above the center of this orifice, and the pressure in the air space above the oil is maintained at x1 above atmospheric. So determine the discharge. Okay, to find the discharge at this orifice. So coefficient of discharge of the orifice is 0.61. Okay, the specific gravity oil or relative density oil is 0.9. Okay, so we apply the Bernoulli equations. Okay, at pressure at 1 here. Okay, inside the tank, closed tank, and the P2 here. Okay, P1 is inside the closed tank, and this P2 here is at the orifice. Okay, the orifice. Okay, so we know that the relative density oil is 0.9. So we know that the density of oil divided by density of water. So we get the density of oil is 900 and the coefficient of the discharge orifice is 0.61. So take atmospheric pressure at 0. Okay, because this is orifice open to the atmospheric pressure. So P2 is 0. Okay, so P1, we get this one, the value. And U1 is the velocity 1. Okay, Z1 minus by Z2, so we get the 0.61 here. So just only have the velocity 2 at the orifice. So we get the velocity at this orifice 6.53 meter per second. And after you get this velocity, so you use the to find the discharge. Okay, Q is equal, okay, Q is equal to A times by V. Okay, so you get this one. Okay, so you get the value of velocity. Okay, look at the example 11. So this is using the sluice gate. Okay. Okay, so compute the flow rate under the sluice gate. Okay, this is a sluice gate. Okay, this is sluice gate. Okay, so the water before the sluice gate flow depth is 2 meter, and before the sluice gate 2 meter, after the sluice gate is 0.8 meter. Okay, so we use the Bernoulli equation. Okay, at point here P1 and the P2 here at after. P1 is before the sluice gate and P2 after the sluice gate. Okay, so P1 here, Z1, V1 is equal to P2 STG plus Z2 and V2 squared. Okay, so this is open to the atmosphere, so that's why the pressure this is 0. And also this also the 0. Okay, because this atmospheric pressure. Okay, 0. So just only have the Z1 and the Z2 here and velocity 1 and velocity 2. Okay, so until you get this in terms of Z1 plus V1 squared over 2G is equal to Z2 plus V2 squared over 2G. Okay, using the continuity equation, okay, relating 1 to 2, so we use the A1 V1 is equal to A2 V2. Okay, considering 1 meter width, okay, 1 meter width for this. Okay, so we get the area of this before the sluice gate, H1 times by 1 times by V1, H2 times by 1 times by V2. So we get the V2 2.5 times by V1. Okay, so after we get this equation, so we use this Bernoulli equation back. So insert the value of the V2 to these equations. So we get this one. Okay, until we get this. We get the value of the velocity 1. So after you get the velocity 1, so we get the Q. Okay, so Q is 4.24 meter cube per second per meter width of channel. Okay. Okay, example 12. A piezometer and a pitted tube are tapped into a horizontal water. Okay, horizontal water here. As shown in figure below, the measure static and static plus dynamic pressure for the indicate water column height determine the velocity at the center of the pipe. Okay, using in chapter 2, so we know that the pressure at point 1 here and pressure at point 2 here is this one. Okay, pressure at point 1 and pressure at point 2. Okay, rho G times by H1 plus H2 for point 1 here. Okay, and pressure at 2 here, rho G plus times by H1 plus H2 plus H3. So we get the P1 and P2 here. So at at stagnation point, velocity is 0. Therefore, velocity of velocity 2 is equal to 0. Okay. So neglecting energy losses, the energy equation at point 1 and point 2 is, okay, using the Bernoulli equation. So you just use the Bernoulli equation using this equation. So you just put all the value here. So Z1 and Z2 is 0 because this is horizontal. So there's no height of the depth of the water. So we get Z1 0 and Z2 is also 0. Okay. So just only have the pressure at 1, pressure at 2, and velocity 1. Okay, velocity 1 inside this one. And but for the velocity 2 is 0. Okay, because at stagnation point, velocity is 0. So therefore, V2 is equal to 0. So after we get this one, so you get the V1. Okay, the velocity at the center of the pipe. Okay, this is the pipe. Okay, this is the pipe. Okay, and this 2 reciprocating tube. Okay, so using the venturimeter, example 13, a venturimeter of throat diameter 0.0676 meter is fitted in a, okay, this is diameter, okay, throat diameter 0.076 meter. So diameter of this one 0.152 meter. Vertical pipe in which liquid of relative density 0.8 flows downward. Okay, flows downward here. So pressure gauge are fitted to the inlet and to the throat section. Okay, inlet, and the throat section. So the throat being 0.914 meter below the inlet. Taking the coefficient of the meter as 0.97, find the discharge. Okay, to find the discharge when the pressure gauge read the same. Okay, this is the value that's given in this question. Diameter 1, okay, diameter 1, diameter 2 here. Okay, pressure at, okay, pressure and density of the fluid here 800 kg per meter cube. CD is the coefficient, relative coefficient 0.97. So area 1, area 2, so you must find from the diameter. So we get the A1 and A2. So after this one, so we use the Bernoulli equation here. Okay, at point 1 and the point 2 here. So we use this one. Okay, this is U. U is also same as the velocity. Okay, U1 or U2 is also same as V1 or V2. So we just put the Bernoulli equation. So we know that pressure at 1 is equal to pressure at 2. Okay, because this is flow downward. So just only have velocity 1 and also velocity 2 plus Z1 and Z2 here. Okay, so by continuity equation, okay, we know that Q is equal to AV V1 times by A1 V2 times by A2. So we get the velocity 2 is equal to U1, okay, U1 times by A1 divided by A2. So A1 over A2, we get the 4 here. Okay, so just put all the value that you find to this equation and then until you get the velocity 1 and also the Q. Okay, discharge. Okay, at this stage, okay, if you don't understand, you can ask in the group. Okay, so using the Bernoulli equation, so we use this, okay, the Bernoulli equation. So ZA minus by ZB, okay, this is A and B. So the, okay, so the flow is upward here. So this is so ZA minus by ZB is negative 0.46 meter. So manometer equation relating A and B. Okay, so relating A and B. So we use this one to this equation, from this one to this one. Okay. So and you get the PA minus by PB, pressure at A to minus by pressure at B. So we get this one. So continue equation relating A and B using the continuity equation. Okay. Previous slides, you first must do the Bernoulli equation. After that, you must do using the continuity equation. Okay, area at point A is times by VA is equal to area at B times by VB. So, and we get the velocity B in terms of VA. Okay, so you get this one and put all the value at this Bernoulli equation. Okay, put at this Bernoulli equation here. So until you get the VA is 1.24 meter per second. So after you get the VA, so you use the Q is equal to A at area A times by VA. So we get the Q 0.088 meter cube per second. Okay. So this is on venturi meter.